Hello everyone, and welcome back to another Eng 130 video tutorial. Now this tutorial is special because this marks the first tutorial video for sample final questions. So before we begin, there's a couple things, a little disclaimer I'd like to give to you all. The first is, I'm going to say midterm a lot. I don't know, for some reason I get final confused with midterm, so if I say midterm, I'm not talking about the midterm, definitely talking about the final. So please excuse that, that's going to happen quite a bit. The second one, which doesn't apply to this example, is I always seem to say shear force bending moment. No, that's actually the correct way. But I get those diagrams mixed up. So for examples of question 2, if you guys hear that, don't be alarmed. That's just me being an idiot, as always. But we're not doing that right now. Today we're going to start with the 2013 final, question 1. Now the 2013 final holds a special place in my heart, because that's the one that I had to suffer through. And it's actually very deceiving, because when you open up to this nice trust question, it actually looks very, very nice. But as you'll see, the remaining questions are actually quite garbage. But we'll get to those as we get to them. For now, we're going to focus on question 1. And that is the trust question. So the trust question for years and years and years, question 1 for years and years and years, always been trusses. So it's probably a good thing to bet that question 1 of your final will be some sort of truss. Now, there's a bunch of different things they can do with trusses, but we'll get into those. So for this question, it's quite simple, and it states, for the truss with the indicated loading at joints C and D and H, as shown in figure 1, A, identify the zero force members. So we're going to go through these one by one, but this is very, very typical truss question. It's always going to be identify the zero force members first. It's kind of what they like to do, because for some reason, I don't know why, zero force members seem to be the hardest with students. So what we're going to do is we're going to go part A, and we're going to say zero force members. And what I'm going to do real quick is, before we get into them, I'm going to show the 2 cases we have to look for when doing zero force members. So I'm going to draw 2 joints. So these are for the 2 separate cases. So I guess I'll label this one case 1 and case 2. And these are the only 2 cases that you guys have to know. So I'm going to label some members. So in case 1, it's very important that case 1 has 2 members. It doesn't matter which direction they're going. So 2 members. And there has to be no load at the joint. So something like this. In case 2 has 3 members, in which 2 of those members are collinear. And what do I mean by that? I mean that 2 of the members are parallel with each other. So it'll be something like this. So we have 2 members like this. And we have a 3rd member coming off at any angle like this. So this is case 1. And then we have case 2. So remember, something about these cases, there should be no loads at the joints. No loads at the joints. So I'm going to write that down because this is very important. No loads at the joints. So very important that we have no loads at the joints, or else you can't use these cases. So for case 1, if this is your case, and you got 2 members at a joint with no load, both of these are zero force members. So it's actually a really nice case because you just cross off the entire joint. You don't have to look at anything. However, I've only seen this case maybe once in a final, and that's because it's just so obvious. If you have 2 members hanging out at the end of a beam, or a truss, I guess, and there's no loads, it's pretty obvious there's zero force. Now, the case that they love to spam you with on the final is case number 2. And that's when we have 2 collinear members, and then that extra 3rd member kind of just hanging out. And in this case, that 3rd member is zero force. And it's very, very easy to prove, because if I were to draw an X and Y axis in this, so we got X, and we got Y, and I would do some of the forces in Y right now, well, that 3rd member would be the only thing in there, and since it's in equilibrium, it must equal 0. So these are the only 2 cases you have to know. And there are some tricks involved with these cases, but we'll go over that in a later midterm. For now, let's just take these cases and apply them here. So if we're looking at this structure right here, I'm going to label the zero force members in red. As we can see, there's only 2 places in the beam that fall under case 1, where we have 2 loads at a joint, right here at E and then we have it over here at A. So those are the only two places that have only two members at a joint. However, because there's going to be reaction forces at E and A, we can say that those are not zero force members. And again, the reason why, if we look down here at our little note, there must be no loads at the joint. And at A and E, we're going to have external loads from the reaction forces, so no case 1 in this case. And that's usually expected. Like I said, it's very rare to see case 1. But be on the lookout. They like to maybe try and sneak it in. So now we have to go, okay, what about case 2? We need locations that have 3 members. So what I'm going to do is I'm going to highlight the locations with 3 members in pink. So we got B, we got G, and we got D. So there's only 3 locations that have 3 members. And if we look at D, well, that one automatically doesn't work because there's a load at the joint. And remember, you can't have any loads at the joint. So we're going to erase D. We know that D can't conclude anything. There's loads at the joint. Now, if we look at B, oh, 3 members, perfect. There's no load at the joint, also perfect. And now we have to look at the next condition is, are 2 of the members collinear? And if we look at B, we see that yes, 2 of them are. We got AB and BC, and those members are collinear. So this actually fits into case 2, and since those 2 members are collinear, that third member must be a zero force member. So this member right here, this BF, we know that that one is actually a zero force member. And if we want to prove it, and well, for proving, it's very rare that they're going to put that on a final, but if they ask you to prove it, if we were to draw a joint B down here, let's just say we have joint B, and we have our 2 collinear members like this. So this one will be AB, and then we have BC, and then coming up here, we have BF, and we were to do sum of the forces. Oops, I don't even know why I drew E. That has nothing to do with anything. If I do sum of the forces and Y is equal to 0, well, what we'll find is that BF is the only thing that's in the Y direction and nothing else. And of course, all this must equal 0, so BF is equal to 0. So we can prove that BF is zero force. If the question doesn't ask you to prove it, like this one right here, just say BF. Don't draw the joint, don't draw anything. Remember, we want to save time. Keep this final going fast. So, perfect. We know that we found 1 zero force member already. Going on to joint G, we first look, are our 2 members collinear? So I'm just going to erase the circle real quick. And we check, oh, yes, there are. We see that FG and GH are collinear like this. So therefore, the third member, which is GC, must be a zero force member. And that meets all of the requirements for cases 1 and 2, so we can conclude that there's 2 zero force members. So what you do here is you just come down and say that members BF and we check our second one, and CG or GC and CG are zero force members. Oops. Again, I'm not the best at spelling. You're going to see lots of mistakes. Are zero force members. Perfect. So I'm going to just draw a quick box around this because remember, finals always want to box your answer. Finals, it's very important to box your answer. They love to almost not take away marks because let's be honest, that's too mean, but you make them more frustrated. You don't want to make the markers frustrated. You want them to have a nice, easy time and go, wow, they did a nice job of their final. So maybe they'll be nicer, something like that. So please just box your answers. And that's the first part. And if we look, that was out of 2 marks. So we're already sitting at 2 out of 10 for this question. Not bad. So speaking of marking, I guess I should probably add, it's just like the midterm. All the questions are going to be out of 10, and then the total of the exam will be out of 40. So just the same marking scheme as the midterm. So we already got 2 out of 10 or 2 out of 40. And again, I showed this with a lot of work. All you guys have to do is say, okay, I see BF and GC. You write those down, and please put them in a sentence. Don't just write them. Put that BF and GC are zero force members, and there's your 2 marks. You don't even have to do any math, nothing like that. 2 easy marks. So what I'm going to do is I'm going to come down, and we're going to start question B. So looking at B, I'm just going to whip out the highlighter. It says determine the reaction forces at A and E. So this question is actually super nice because typically they won't give you, well, they're going to give you marks for it, but they're not going to ask you to do this. This question is kind of holding your hand through the process. I've seen some finals where they just give you a truss structure and say solve it. And to solve it, you'll need to do the zero force members in addition to finding the support reactions, but it won't directly tell you. So this question's kind of nice, holding your hand through it. So if we're solving reaction forces, the first step is always going to be draw a free body diagram. So we're going to come down here, and we're going to say free body diagram, or FBD. Very important, even though this one's pretty simple. We got to come down here and say, okay, got free body diagram. So we know I got 1, 2, 3, 4, like this. We know that it goes up by 4 at some locations, like this. And we'll bring this down here. This one comes across. I know that this is probably the most boring part of the videos to you guys, is watching me try and draw a free body diagram. I can only imagine how ugly this would look if Notability didn't help my butt out. Alrighty, so here's the simple truss structure, and then we're going to add our external loads. So starting with the actual external loads, not the reaction forces, we see that we got a 6 kilonewton load up here, and this one's really sneaky. A lot of students at this point in the course are only used to vertical loads, because besides trusses, we only really deal with loads going up and down. So be careful of horizontal loads. They can come back and bite you in the ass. We see that we got 2 vertical loads at these joints here, which are 8 kilonewtons and 10 kilonewtons. And then finally, we have our reaction forces. So over at A on the left side, we have a pin. So we know that we're going to have 2 forces. We're going to have a vertical force, and we're going to have a horizontal force. And you guys can label these whatever you want, but I like to just take whatever the joint is, so in this case A, and I'm just going to put AY and AX. And on the other side, over at joint E, we have a roller, so it's just going to be a single vertical force. So it's going to be just a force upwards, and since it's at E, I'm just going to put EY. So like this. A couple other things that you should add for trusses is just the joint names. So we got A, and we got B, C, D, E, and then we have F, G, H on the top. Perfect. And finally, it wouldn't be a free body diagram without some dimensions. So we know at the bottom, well, it's going to be split up into 4 segments, and each of them is 3 meters. 3 meters, 3 meters, 3 meters, 3 meters. So this is quite boring. But looking at this truss, it was very, very nice. It's a very simple truss. And we got 4 meters high. But very simple truss. Again, this final was kind of an ass because it disguised itself as a nice final. You turn the page, oh look, the most simple truss you can get. Even the labs weren't this hard. But then when you turn the page to the rest of the 3 questions, it got pretty gross really fast. But you guys will see that, especially question 3, which to this day, I have not forgotten. I remember sitting through that final, turning the page to that question, thinking like, oh shit, this question's going to ruin me. And spoiler alert, it did. It was terrible. And I remember it till this day, which was, well, 2013, now it's 2019, 6 years later. Not a lot of fun. But back to support reactions. I know you guys don't care about my story. We can do a couple of things here. So we see that there's a lateral load, and we see that we have a horizontal reaction force. So I'm going to start off with say, okay, if we take some of the forces in the x direction is equal to 0, what we find is we have AX, and it's going to the right. So we assumed it going to the right, so it's positive. And we have plus 6, because we have the 6 kilonewtons at top, also going to the right. But that's it. So it's in equilibrium. We can say it's equal to 0. So when we solve this, what happens is we get AX is equal to negative 6. But we know that AX is not actually negative. It just means AX is 6 kilonewtons, but the direction is opposite of what we assumed. So we assumed it's going to the right. Well, it's actually going to the left. So we're just going to put a little arrow there indicating it's actually going to the left. So there's the first one, nice and easy. But now we start to run into a little bit of trouble because we got AY and EY. So if we were to take some of the forces in Y right now, well, we're not going to get anywhere because we're going to have two unknowns, only one equation. So it's always best before we do that to take the sum of the moments. So if I go sum of the moments, and then we have to pick our point. So I usually like to take it about the pin. It always seems to work well for me. So I'm going to go sum of the moments around A is equal to 0. So I'm just going to go through I always want to say beam, but it's a truss. I just go through the truss and find out all my forces. So I got 8 kilonewtons. So I'm just going to put 8. It's a distance of 6 meters away. So the 3 plus the 3. And if I look at the rotation, I see it's going to create a clockwise rotation. So therefore, this is negative 8 times 6. So we're good. We move on to the next one. We got 10. It's going the same direction as the 8, so we know it's going to create a negative moment, so minus 10. And then its distance is going to be 3 plus 3 plus 3, so this one's going to be 9 meters away. And then at the very end of the beam, we got EY, and this one's going the opposite direction, so we're going to go plus EY. And this one's times 12 meters. And most students would look at this and say, okay, perfect. We got our moment. Well, actually wrong. And this is why I say that lateral force is really sneaky, because there's actually a moment created by the lateral force. So it's going to be 6. And it acts at a distance of 4 meters above point A. So we're going to add the 4 in. And we know all this is equal to 0. But the last thing that we have to do is realize that the 6 kilonewtons will also create a clockwise moment. So it's going to be also minus 6. So we have a nice equation. We only have one unknown. We can solve for all this, and what we'll find is that EY is equal to 13.5 kilonewtons. And it was a positive answer, so our assumed direction of up is actually correct. So we can just keep that as a little arrow up, and we're going to box it like this, and we're good to go. So now we know 2 out of the 3. Well, we can just go to our sum of the forces in Y to finish it up. So if I come down here and I go sum of the forces in Y equal to 0, I can just go from left to right on the beam. So looking at the very left side, well, we got AY going up. And then coming across, we see that we have an 8 kilonewton force and a 10 kilonewton force going downwards. So minus 8. Minus 10. And then at the very end of the beam, we got EY going upwards, but we know EY. And EY is 13.5. So plus 13.5, and that's also, it's equal to 0. So it's very, very easy to solve for, and we get AY is equal to 4.5 kilonewtons. And it's also a positive answer, so our assumed direction of up is correct. So I'm just going to put up. Put a little box beside it. Again, please box your answers. Very, very good practice to do on exams. So we solve for 3 reaction forces. If we look up at B, also complete. So the first 2 parts of this was actually very simple, very quick. Now we're going to get into something that's more kind of truss orientated. And that's determine the forces in members CD, CH, and GH using the method of sections. So the method of sections, as we'll talk about, is when we have to cut the beam, or cut the truss, and analyze all the sections that we cut. And then, of course, this goes without saying, clearly indicate if the members are in tension or compression. So remember, if we stick to a certain sign convention, which I like to use, and that's assuming all of the members are in tension, so all the forces are pointed away from the joints. If we get a positive answer, it means it's in tension. If we get a negative answer, it means it's in compression. So we're just going to keep a lookout for that. So, quick reminder, method of sections, that's when we cut the beam. That's when we cut the beam and we analyze each force that we cut using equilibrium. It's not when we look at each joint, that's the method of joints, but rather it's the method of cutting the beam, cutting the truss, looking at all the members. And the trick I like to do for this, because the hardest part of this is going to be determining your cut. So this beam, as you'll see, it's pretty easy, but for other beams, it could be a little bit questionable where you want to cut. Because it doesn't tell you. You're going to have to kind of figure it out for yourself. So what I like to do is I like to highlight the members in the question that I need. So I need CD, CH, and GH. So I'm going to come down to the beam now, and I'm going to highlight them. And if I look, I see CH is right here, or GH. I got CH, and I got CD. And what I like to do personally is I like to try and cut through all of those members. So I'm going to make a cut. Oops, not using the highlighter. I'll just use the regular pen. I'm going to cut straight down like this. So what happens after I make this cut is all the members that I cut, they turn into forces, single forces. So looking at the left side, these three will turn into forces like this. And then on the right side, they'll turn into forces like this. And now it's up to us to choose which side we want to analyze, because it doesn't matter, both will give you the same answer. And looking at the right side, it's a little less than the left side. So I'm going to choose the right side. So what I like to do for this is I'm going to come down and I'm going to go part C. And the first thing I'm going to put is I'm going to put cut the truss. I was about to say beam again. Cut the truss. And then what you're going to have to do after you cut the truss, and this is very important, you're going to have to draw a free body diagram. You can't just say cut the truss and then start doing equilibrium equations on the figure 1 that they give you. They're not going to give you marks for that. They're going to see your new free body diagram after you cut the truss. So the way I like to draw the free body diagram after I cut the truss is I'm going to draw the members that I didn't cut. So looking at this truss, the members that, oops, I'm not going to use the same highlighter, I'll go to blue. The members that are still left intact after the cut are these ones right here. So it's just actually a triangle. So I'm going to come down here. I'm going to say, okay, I have a triangle left. So something like this. This, and then this over. This here. And then I'm going to come up and say, okay, on this triangle, I still have 3 lateral loads. I got my 6 kilonewtons, my 10 kilonewtons, and then of course, and this is very important, I have the reaction forces at E. So I'm going to start by placing the 6 and the 10. So I'm going to come here and say, okay, I got 6 kilonewtons coming at the top. I got 10 kilonewtons coming down this way. And then I got a reaction force at E, which I remember was up. So we're going to put a little force coming up here. And we're going to check, and we see that EY is equal to 13.5 kilonewtons. So I'm going to put 13.5 kilonewtons. And then I need to put all the members that I cut. So I'm going to do this in a different color so you guys can see very clearly. If we look up here, I cut through GH at the very, very top. So I'm going to have a force coming out horizontally, and this one's going to be GH. At the very bottom, I see that I cut through CD. So I'm going to have another horizontal force down here coming straight across. And this one's going to be CD. Oops, I didn't draw that very nice. Let's see if I can go back and make this a little bit nicer. And then kind of the pain in the ass member that we have is going to be the diagonal one, which is CH or HC. It doesn't matter which order you put them in, we know what you guys are talking about. So this one's coming down kind of like this. So this one we're going to see is CH. Alright, so now we got our members. And then remember, a free body diagram should always have some dimensions. So I'm just going to dimension this real quick. We know that the bottom 3 meters. We know that the height of this is 4 meters. 4 meters. And then since we have a diagonal member, it's good to put its little triangle, its little relationship right here. So we know that this is going to be 3 and 4. So therefore the other side must be 5, just the hypotenuse. And then, like I said, it's always good practice just to label the nodes on the joint, or the joint ID. So we got D, H, and E. So I'm going to come down here, D, H, and E. So if we take in the sum of the moments, we can clearly show which point we're taking the moment about. And that's very important. So if I didn't have these on and I were to say sum of the moments at D, you guys might lose half a mark or something, because it's very important to show very clearly where you're taking those moments about. But moving on, looking at this, well, this is just another free body diagram. We got 3 equilibrium equations, and looking here, we have 3 unknowns, so we can solve for it. So the first thing that we're going to say, okay, well, if I take some of the forces in X right now, I'm not going to get too far, because I'm going to have GH, CH, and CD all in one equation. So three unknowns in one equation, that's a little much. So we're going to have to think of other methods to try and figure out to solve these without getting too messy. So looking at this, I noticed real quickly that CH is the only one of these members that actually has a vertical component. So if I start off with sum of the forces in Y is equal to 0, well, looking at this, I'll start with my external loads. I got 13.5 kilonewtons coming upwards, so 13.5, and then I got 10 kilonewtons going downwards, so minus 10. And then the only other thing I have left for in the vertical direction is CH, and it's going downwards, so we're going to go minus CH, and we're going to want the vertical component of that. So it's going to be 4 over 5. So in this bracket and equilibrium, everything must equal 0. So when I solve for this, I get, and I'm going to show the exact answer right now so you guys can see exactly what I do. When I solve for this exactly, I get CH is equal to 4.375 kilonewtons. So this is a positive answer. So when I'm putting my answer, I go therefore CH is equal to 4.38 kilonewtons. And since it's positive, we put this little t here to mean tension. And that's what it means up here in the question at the bottom here where it says clearly state if the members are in tension or compression. We have to put that little t or that little c to indicate so. So coming down here, this is one of my final answers. So let's put a nice box around it to show everybody this is exactly what it is. Perfect. So now I got one of the two, but remember if I go with sum of the forces in X right now, well, I'm still going to have two unknowns, only one equation, so we're going to hold off on sum of the forces in X. So the next equation we have, just by default, because we already did sum of the forces in Y, is sum of the moments about a point is equal to 0. So if I look at this, I want to cancel out either GH or CD. Now, I could take the moment either location. Either location is going to give me exactly what I'm looking for by getting one of the unknowns, but if I take the moment at D, well then I got CH there, and CH is going to be kind of a pain in the ass. I don't want to have to deal with anything diagonal. So in my opinion, I think it's better to take the sum of the moments at H, at the pink point right here, because it gets rid of that diagonal member altogether. So for me, I'm going to do sum of the moments at D, or sorry, I just say I'm not going to do it. I'm going to do it at H, and then I say D, like a dumbass. D for dumbass. So sum of the moments at H is equal to 0. So if I look at this right here, it's actually funny. A lot of the forces act through H. GH acts through H, the 6 acts through H, CH acts through H, and then the 10 kilonewtons at the bottom also acts through H. So the only thing I'm going to have in this equation is going to be the 13.5. We're going to have the 13.5, which acts at a distance of 3 meters. And we see it creates a counterclockwise rotation, so a positive moment. And then we got the CD, which is going clockwise, so minus CD. And this one acts at a distance of 4 meters. And all of this is equal to 0. So there's actually only two components to this equation. It's pretty nice. And when I solve down here, so this is the exact answer, I get CD is equal to 10.125 kilonewtons. So when I'm writing this answer in the final, I'm going to put therefore CD is equal to 10.1 kilonewtons, and then since it's positive, it means it's in tension. I'm putting that little t just to help show this is in tension. We're going to stick with that. So we're going to put this like this. We're good to go. So now we can go to our last equation, because originally it had 3 unknowns, but now we solve for 2 of the 3. It only has 1 unknown now, and that's sum of the forces in X must equal 0. So looking at this equation, we're just going to go kind of left to right, and at the very left spot we see that there's 4 of them. We're going to have 6 kilonewtons going to the right, so we're going to have 6. And then we have GH and CD both going to the left. So minus GH minus CD. Now, if we look, we also have CH, or a component of CH, also going to the left. So minus CH, and its component's going to be 3 over 5. And if we look up to the top, those are my only ones going in the x direction. So this must be equal to 0. So as you guys can see, when we originally started this, it'd be a real pain in the ass because we got 3 unknowns. But now if we look up, well, we know that CH is 4.375. So I'm just going to put 4.375. And then CD over here is 10.125. 10.125. So now we only have one unknown, and when we solve this equation down here, we get GH is equal to negative 6.75 kilonewtons. So since it's a negative answer, it means that this member is actually in compression. So when we're writing the answer here, we go, therefore GH is equal to 6.75 kilonewtons, and we go in compression. So you see how I left that answer positive, but then I just put a little C at the end to indicate it's in compression. So I'm just going to highlight this right here. Good to go. All of our answers are boxed. They're all clearly stated. I look up at the question. Well, I solved exactly what I wanted for, and there we go. That is question 1 of the 2013 final. And if we're looking at kind of just talking about trusses, this is, I'm going to have to say, probably one of the easiest truss questions you guys can ever get. The cut was very obvious. It kind of held your hand by telling you to identify zero force members, determine the reaction forces. Yeah, pretty easy. As you guys remember, some of the other finals, like I think 2016, it just said, what's the maximum load a truss can take? That's it. It didn't say anything about zero force members or reaction forces, anything. So looking at trusses, kind of the bare bones easy question. But we're going to do another example where it gets a little bit tougher to kind of help show you guys what to expect in the final. But this is a good review of zero force members as well as the method of sections. So hopefully you guys kind of learned something. And yeah, I think this concludes this question. Thank you guys all so much for listening. I will see you guys in question 3. And yes, question 3, we're going right to friction because question 2 of this final has something called internal hinges or internal pins, one of the two. It doesn't really matter what you guys call it. But that was not covered this year, and this year is 2019. So if in 2020 or beyond and it is covered, I apologize. I'll do a video next year, I guess. But yeah, so don't worry about question 2 of 2013 for those in 2019 and maybe beyond. We'll have to see. So yeah, thank you guys again so much for listening. I'll see you guys in the next example.